Welcome back to our seminar series. As you may remember, this year our theme has been mean curvature flow with surgery. Now, that was elected by popular demand. It's been quite a long year, but we're finally at the point where we can actually do mean curvature flow with surgery. It's my pleasure to ask James to carry this out. This is perhaps one of the most daunting things we're going to do this year, but James has kindly agreed to do it. So thank you, James.
Thanks, Tim. Yeah, so as Tim said, it is very daunting. A lot of the details are quite difficult and it gets pretty technical. So you have to forgive me for skipping over some things, but please, interrupt me if you have anything more insightful than me to say, or if you have any questions, of course. So surgery on necks. So last time we detected necks. Okay, so I guess previously we showed that curvature necks imply that there's some sort of topological neck. So you can parameterize locally by a cylinder. Okay. And so today, we're going to show that we're going to cut into these necks. Okay, so we're going to show that we're going to develop a surgery technique on necks that preserves essentially to convexity, or this more general class we've been studying. Preserving, well, not more general, maybe more slightly smaller class than to convexity. So preserving this CR alpha. So remember, this is, so M is in C alpha, and alpha is just a tuple of 3 numbers. If and only if the following hold. 1, it's got this kind of pinched to convexity going on. 2, we want it to be strictly convex in a controlled way. Mean convex in a controlled way. And 3, we want the volume to be controlled as well. Okay, so we want to cut these necks that we found, but we don't want to just do it willy-nilly. We have to make sure we can preserve these properties so we can continue our mean curvature flow. And recall that we already showed that this is preserved by mean curvature flow. So at the end of today, we will have that it's preserved by mean curvature flow with surgery. Before we do that, we need to take these topological necks we found and we need to pick a very nice parameterization for them. So I'll call this the canonical parameterization. Let me set up some notation. So we've got a hypersurface. We have some parameterization of some cylindrical parameterization. Okay, so this is a local diffeo. And let G be the pullback metric on the cylinder. So I'll write that. A very important function for us is going to be this sort of mean radius function. So it maps from the interval into R plus, and it's the average radius. So what does that mean? Well, if I take a volume of one of these cross sections in this pullback metric, this is going to be the volume of the standard sphere times Rz to the n minus 1. Okay, so this gives us the average radius at each cross section. And let's let G bar be the standard metric. Terrible. Standard metric on the cylinder. Okay, so that's just setting up some notation, and then we have a very long definition. So we say N is a normal epsilon K hypersurface neck if, okay, so first of all, this is like 3 definitions in the paper, but I'm going to put it all into one. So I'll call this AI. So first of all, when we can formally rescale the pullback metric, this is close to G bar in the CK norm, epsilon close. Secondly, the radius function, the average radius function doesn't grow too quickly. So I can bound this. This is for 1 less than or equal to J, less than or equal to, less than or equal to K. So we can make this happen. I'll call this one BI, and this is kind of what they call a normal. This is the part that's called the normal parameterization. This is called something like an intrinsic curvature neck. So this is what Hamilton would have defined, or an intrinsic geometric neck, because we're not using curvature yet. But just keep in mind, all these conditions are basically to get us existence and uniqueness of this parameterization. So we just want a strong enough thing to give us this canonical parameterization. So the image of these cross sections, we want to arrange so that this has constant mean curvature. Okay. Secondly, we can also arrange that if we just restrict to this to these cross sections, I'll call the image of these cross sections sigma z. Okay, but say we restrict to here, then this is a harmonic map. Equivalently, the identity on the cylinder is a harmonic map between the pullback metric and the standard metric on the cylinder when we restrict to the spheres. A little subsection of here is if n equals 3, we want the center of mass of the metric on the cross section to be the origin. Now, I think the reason we make this distinction here is because basically to get these harmonic maps, you apply the inverse function theorem. For n equals 2, it turns out you can you've got this degree of freedom that comes from conformally rescaling. Okay, so I think you can conformally rescale these harmonic maps in dimension 2, but you can't in 3 or higher. And so that's why we have this extra condition here on the center of mass to get our uniqueness.
Wait, sorry, James, doesn't that mean that, should it be if n is equal to 2 then? You said it was different if n was 2, but you said that you have to do this if n is 3. Is that...
Sn, so it's a harmonic map on the sphere, so the sphere is S2 when n equals 3.
And and S2 is the time when you've got to be more careful.
Yes. Yeah.
Okay. Does everything just break
James,
down if n is 1? Sorry, if n is 2?
In this case,
like what happens if you're just doing it with circles? Probably nothing good.
Good question. Yeah, probably
completely different.
Good. I don't know. Yeah. Probably a completely different realm.
I mean, Ben mentioned last time that this recognition of topological necks doesn't hold, right?
Yeah, exactly. Because you can wrap multiple times or something, right? When you've got an S1.
So James, so what you're doing here is you have something which looks intrinsically very close to a cylinder, right?
Yep.
Because you say the average radius is it doesn't change too much, and then the metric is close to the canonical metric on the cylinder, and then you want to have like a canonical parametrization of the cylinder.
Yes. Yeah, exactly. So yeah, so that's what these A's are. It's saying it's close, and then these B's are kind of fixing the exact parameterization. It'll be unique up to symmetries of the cylinder. So yeah, you can make this happen essentially by the inverse function theorem. I know that's not a very nice answer, but that's all I've got. The third one, this is kind of fixing a scaling of our Z parameter. So if I take the volume in the pullback metric of little sub-cylinders, then this is the same as integrating over the average radius to the n. Why not n minus 1? Well, because this is going to, this gives us a scaling invariant thing, okay? And that's going to fix the scaling of Z, okay? So it means we can compare necks at different scales. Okay, again, that's going to help us. This last one is probably the most mysterious. So for any killing vector field, so infinitesimal rotation of the sphere on these cross sections, we want that the integral over the cross section of the standard metric applied to this v bar and u, this equals 0, where u is the unit normal, to the cross section, but in the image. Now, what's this doing? I mean, intuitively, to me, this is telling me that, you know, if you have a canonical parameterization, you could maybe twist it, right? You could twist things around, and basically this is stopping you from having that degree of freedom. You're kind of fixing that. Again, it's kind of vague, but
James, just to be clear, is that a killing vector field with respect to your reference, like the canonical metric?
G bar, yes.
Yeah, okay.
Almost there with the definition. We also just want the second fundamental forms to be close as well. So this is essentially what we had last time. So up to scaling by this conformal factor, we have this. Okay. And so that's what that's going to be, you know, our official canonical parameterization for these necks that are close to a cylinder. And so Hamilton kind of introduced this and proved, you know, existence, uniqueness, you know, maximal existence of maximal normal necks, which I'll define a little bit better. And so the main theorem to keep in mind is that if you take a epsilon, k, and L big enough, say greater than or equal to 10, then you can find these other epsilons and k's such that if, so now we go back to, we want to detect one of these normal parameterization, these necks from a curvature neck, right? So if the curvature is epsilon k L cylindrical around P. So what does that mean, right? So that means that W minus W bar is less than epsilon, and it's not almost parallel. And this all happens in the ball of radius L around P. Okay. So if we have the curvature looks like a cylinder, then P is at the center of one of these of a normal epsilon k hypersurface. Yeah. And then which is in turn inside a maximal normal epsilon k hypersurface neck, unless M is actually already diffeomorphic to S1 cross Sn minus 1. So what do I mean by maximal? I mean, you could define it as follows. You say N prime, so another neck, is maximal if, so whenever you can write it as N prime equals N after G, for G, a local diffeomorphism of the cylinder, well, that means that G has to be already onto. Okay, so you can extend these things, you can extend these necks out, you can glue them together because the scaling is right. So you've got these normal necks. And if you're not already diffeomorphic to S1 cross Sn minus 1, then you can say for certain that you're inside a maximal one, a maximally extended one. And you can see where the problems would arise if you were in S1 cross Sn minus 1. You want to maximally extend a cylindrical parameterization, you're going to run into problems once you get around the other side of this S1 factor, right? So that's why we want to exclude that case. Okay, and the proof just follows from what we did last time, right? So we had this curvature neck, and then we showed that if locally the graph of like over a cylinder, and that's close with a small yeah, it's locally the graph over a cylinder, and the function is small in the sk plus the ck plus 2 norm, right? So it essentially follows from last time, but this is like the thing we're going to use, like this is our main machine. Because now we're going to detect when the things are, and then we've got a nice canonical parameterization showing up. Okay, so is there any questions there?
Yeah, James, I haven't quite formulated this question yet, but I guess it's to do with the maximality. Maximality is all about, you know, extending your CMC foliation more or less. If you've got a maximal one, what does that mean at the boundary? Does that mean you stop being cylindrical?
I think you probably stop being epsilon k cylindrical, so to speak. So you no longer satisfy these bounds, for instance.
Okay, so that's what, because if there's a boundary of this thing, that means that something went wrong, and I guess in this case it just means that you don't have your estimates anymore.
Yeah, I think so. I think your curvature just gets too far away.
Yep. Thanks.
Yeah. No worries. Okay. Yeah, because I think these estimates here allow you to, you know, get these CMC foliations and stuff. But yeah, I didn't go too far into the details on that one. Okay, so let's do some surgery. So we've got a map. So cylindrical, from now on, I'm always going to assume that these are the nicest they can be. So you've got this normal parameterization. Let's take a fixed Z0 in AB. And let's say it's sufficiently far from the boundary. So let's take Z0 minus 4 lambda, Z0 plus 4 lambda is inside this interval. And we'll pick this later. Okay. Ultimately, we want to make this large. And we have a couple of other parameters we want to fix. So we fix some tau between 0 and 1 and some b, let's say, bigger than 10 lambda. Okay. And let's also take CZ0. I will draw a picture in case you're worried. So n minus 1, or let's just say cross R, to n+1. Let's let this be an approximating cylinder. Okay, so the radius is equal to, so the radius of this cylinder is r0, which is just r, the average radius at z0. And the axis is parallel to the average unit normal of the cross section. Okay, so it's just the cylinder that lines closest with our surface at that point. And so let's do the standard surgery procedure. So this happens essentially in, I think, 4 parts. So S n+1. So we have this parameterization.
James, sorry to interrupt. Could you? Why is this called standard surgery?
I'm not sure. That's just what they called it. Good question.
I think because there's many choices,
So
they just pick some choices.
so this one's obviously more standard than the other choices.
No, I think because when they do the surgery, they have to fix some choices. And the ones they fix, they're calling this. I think that's the idea.
Yeah,
Oh,
eventually we're going to make B very large and things like that.
So standard means the choice that works for them?
I think so.
Okay.
And this should be Sn-1. So further than 3 lambda either way is going to stay unchanged. So the surgery is very boring there. And the idea is we're going to replace the ends. We're going to cut it there, well, cut it a little bit further and replace the ends with some end balls. Okay. So B, we define this kind of this function that we're going to use to start bending our surface in to begin replacing it with end balls. So let's take this as r0, and the function we're going to use is exponential of minus b over z minus lambda. Okay, also I'm only going to care about the left one here, and the right one is analogous. So let's define that function. And then our new parameterization, n tilde, we're just going to take n, and we're going to subtract off our factor of tau times u times the normal of n. Okay, so we just bend it in along the norm. And we do this in such a way so that it becomes strictly convex on 2 lambda to 3 lambda. And let's also do the same to our cylinder with the same function. So how does this process work?
So you said Z0 equals 0, is that right?
Yes, sorry. So let's just simplify things and say Z0 equals 0. That's, yeah, I forgot to mention that. So say we've got a close to cylindrical surface. I'm going from 0 to 4 lambda. Okay, so it doesn't change up to lambda. Nothing happens. Okay, and then what do we do? So first I'm bending my, let me draw in my approximating cylinder as well. Say it looks something like that. It's a cylinder. Okay, so I'm bending my my surface in via this function u. Here. And I'm doing it so that once I get to this region, it becomes strictly convex. So, I mean, it does something like that. Okay, and then something similar here. Okay, and I do the same thing with my cylinder. Maybe I'll do this in blue. So my cylinder comes down like this. And maybe on this side it comes down. Okay, so that's that process. And then C.
Sorry, James. When this picture is Z actually? Because you said you are doing the left side, and then you said Z is 0.
Yeah. So
but this seems like you're doing the. But that's a right. There's the right side, and you say you are doing the left side.
The right side's over this way.
Yeah, but I mean, on the left side there's the manifold, and you wanna like attach a cap to it. And I thought that the cap was like before the Z. Not.
What am I doing here?
Do you know what I mean?
Yeah, isn't Z0 the center of the neck? So shouldn't it be going like? I'm not sure, but like.
This is the center because we're attaching the cap here and then a cap over here on the left as well.
I thought we are doing the cap along Z0, and then we are doing caps on the right and left. But this seems like we're doing the cap like after Z0.
I see what you're saying. Okay, let's pretend all of this is reversed.
What?
Yeah, no. Yeah, so I've drawn the picture backwards. Yeah, I know what you mean. So what I should do is have what should we do? Let's make it simple and do this. Okay.
Okay.
Pretend the whole the whole
okay.
So yeah, I mean, yeah, the idea is left or right, it doesn't matter, but the idea is that's what we're doing. Yeah, true. I'm not quite sure how I got things mixed up there. Anyway, so the next step is to kind of interpolate these things. This is not meant to be a super. I mean, I'm hoping it's at least slightly lining image. So we take a smooth cutoff function. Okay, with yeah, no, I'm not sure. So essentially we want the cutoff function to look like 1 in this region. So this is phi. It's going to be 1 in this region, and then it's going to go down to 0 here. And you can arrange this so that the derivative's nice and bounded, and then you interpolate. So you interpolate your parameterization. Between the bent one and the cylinder. Okay, and so it's not super easy to see, but the thing we end up getting, I'll draw in red, is we want to go on the pink first until we get to lambda, and then we kind of interpolate up to the blue, and then same thing here, right? Yeah, it's not a great image, but the idea is that this becomes actually symmetric in, I guess this is going to be -4 lambda to -3 lambda now, so to speak. So that's why we interpolate with the cylinder. We want something actually symmetric. And then finally we change U to U hat on I guess now we're calling this -4 lambda to -3 lambda. So that basically now we want to just modify the rest of it so that it turns into a spherical cap, right? So TU hat goes to R naught as Z goes to Z1. And this will ensure that, I guess this has to be minus 4 lambda now. Something along those lines. I'm sorry for completely reversing the orientation. But yeah, the idea is now we've got a nice axially symmetric, strictly convex thing. You can attach a cap here in a controlled way. And by making sure that everything's, everything's nice and small, this cap will have a nice bounded curvature. Okay, are there any questions about that process? So it happens in kind of 3 steps. So you bend the surface so that it becomes strictly convex. You interpolate with a cylinder, and then you have an axially symmetric, strictly convex thing that you attach a cap to, and you do it in such a way that you control the curvature.
James, sorry to be annoying. The idea is exactly right. I think you can fix it up just by changing the order of your parameters there. So
Yeah.
that green line's the center of your neck, right? The vertical green circle.
This one here?
No,
No. Yeah, this is the center of the neck. So
and
what I think
that should be a Z naught. Is that right?
Yeah.
And so if you just put the Z naught there and then put the lambdas going the other way, that sorts everything out.
Yeah. I think what I wanted was, wait, let me just check. I think I wanted Z naught minus 4 lambda equals 0.
Okay.
I got that wrong. Yeah.
But yeah, sorry to
no, yeah, I completely I got lost there. Where did they say?
Because otherwise the picture is totally fine. So I don't want to get you bogged
Z naught minus 4 lambda equals 0. So now this is Z naught, and now the picture makes way more sense.
Yeah.
Yeah. Sorry, everyone. Yeah, I got my wires crossed there. So now let's take the minuses away, and everything works.
So why did you need all these other conditions, like the map is harmonic when restricted to the cross sections, and the foliation is a constant mean curvature?
So I mean, that's just going to fix a unique parameterization for your neck, and that's going to come into play when you find a maximal one, for instance.
Yep.
Because you want to be able to compare different necks that overlap and glue them together, for example. And if you have a canonical parameterization, it's much easier to do that, I think.
Okay.
And it might become more technically relevant when we actually do the flow and detect a neck as well. I'm not sure.
Yeah, in fact, James, I was going to ask you something similar to that. Whether the fact that all of these SN-1 copies have constant mean curvature, does that come in anywhere except that it makes this parameterization canonical?
A great question, which I don't know the answer to. Yeah, sorry. As far as I can tell, I've only used. Yeah, sorry, go on.
Can I just add one thing there? I think it's also important because you want to keep track of the diffeomorphism type here as well.
Oh, true.
So that's a really crucial part of having an explicit parameterization for these necks.
Good point. Yeah, maybe the topological. Yeah, that's true. Anyway, so thanks for getting me out of the woods on that one. So now, I mean, the technical bit is to show that the curvature doesn't change too much and that you can preserve this class of manifolds, right? So let's do that. Are there any other questions on this process? I know I kind of fudged the numbers, but you take your neck, you bend it so it's strictly convex, you interpolate with a cylinder so that it's symmetric, then you attach a cap. Okay. So, yeah, so we want to do curvature. of, say, this parameterization, right? This new parameterization, which is n minus tau u times the normal. Okay, so this is a very hard part. And essentially, we want to estimate the eigenvalues of the second fundamental form. So I'll just state the key proposition that you want to show, which is that if you take the fundamental form, second fundamental form of the new one, and you subtract off the following, so you take the original second fundamental form, you have a tau in here. Remember, tau is one of our parameters. You can estimate it. So you've got the second derivative of u showing up. These turn out to be important that they show up. So if we look at that difference there, this is bounded in a very controlled way. So we've got c tau epsilon u prime plus c tau squared. The tau squared is very important, r to the minus 1, and then you have the c2 norm of u. Okay, and so if u is chosen smart enough, you can control the second fundamental form. Okay, so the proof ingredients, so to speak, and I won't go into too much detail, but the ingredients, first you want to estimate the metrics in relation to each other, okay? Or more specifically, you want to estimate this quantity. And then you essentially want to estimate the normals, how the normals change. And then from there, you use, you estimate the second fundamental form. So how do you write this, right? Well, this is minus nu tilde, so the normal of the new surface, and then you take the second derivative with respect to ij of the n tilde. The n tilde you can, the second derivative of n tilde you can work out, right? Because we have an explicit formula for it. In several steps that I won't do here, but it compares to the original second fundamental form in the following way. You get exactly what shows up in the proposition, so minus tau u plus, and now there's an extra term with a bij. This is kind of a complicated term involving derivatives of the original n and derivatives of u. And so you can see that once we control, say, the difference of the normals, we can control this. And then you have to trust me that you can also control this. And you can do this in a precise enough way to get this bound with this explicit dependence on tau, which is important. Okay, and you're explicitly using the condition that the second fundamental form is close to that of a cylinder. And that's why the R is showing up as well. Okay. Yeah, I bashed my head against the wall for these calculations for quite a while, and they're kind of, yeah, they're pretty tricky. The two I've stated are not too bad, but the rest, yeah, I haven't quite figured out the details. But the point is, right, that we can estimate the second fundamental form in relation to the original second fundamental form, but in this controlled way, depending on derivatives of u. What we do now is, as I said, we take u of equal to r naught, and then this function I mentioned before, minus b over z minus lambda. Let's call this f. And then we have a lemma that I would probably give to first or second year students. For all delta larger than 0, maybe third year, and lambda larger than 0, there exists a b large enough so that I can control the derivatives of f in a very nice way, meaning f, for instance, is bounded by the second derivative. I get this relation for the first derivative. And finally, the second derivative is also bounded by tilde. Okay, so I can make this, I can basically make everything as small as I want. So that's quite nice. And then,
oh, sorry, James. What was Z was the independent variable in that, right? Where is Z living?
yes, sorry. Z is in AB.
Okay.
Yeah. So this is your scale invariant factor on the axis of the cylinder. And so what you get is, say for all theta bigger than 0, lambda bigger than, say, 10, you can choose k big enough, epsilon small enough, tau small enough, and b large enough, such that, okay, and now I'm going to estimate the eigenvalues of my second fundamental form. I'm just rewriting basically the previous proposition, but in terms of the eigenvalues, because I think it looks a little bit nicer. Lambda 1 is, of course, special. Okay. So you get these bounds, and the idea is we can make theta as small as we want, which is really, really nice. And so finally, a corollary, which I'll do part of the proof of, just because I think it's slightly insightful for why we even want these estimates to pop up. We get a few things. The new mean curvature increases, which is good. This thing remains too convex as well. In fact, okay, so it doesn't follow from any computations I've done here, but you can also control the volume forms in essentially, you know, similar tricks to above. And finally, in fact, you can control this pinching as well. So this pinching increases. Okay, this is on this interval. Of course, we don't care about anything up to lambda because we're not changing anything on there. Okay, and so maybe I'll just very quickly do the proof of 2 using these estimates that I've essentially black boxed. I'm very sorry. Because I think at least this enlightens you on why you want to do it. So lambda 1 tilde minus lambda 1 plus lambda 2 tilde minus lambda 2. So I want a lower bound on this. So I know that the difference, so for the lambda 1s, say, I can bound this below, by minus this plus this stuff, right? So I get a minus theta tau naught d1 squared u, and then plus tau naught d1 squared u, plus tau naught u lambda 1 squared. Okay, so that's from the lambda 1 tilde minus lambda 1. Same thing with the lambda 2s, except I have to use this estimate here. Again, I get a minus 1 of these, right? So I get actually 2 of these. And I get another factor of I get a factor of lambda 2 squared. So I can put plus lambda 2 squared here. And now you can see why it was really important to have the theta over here, because I can make this larger than or equal to, well, let's say this, as long as theta is less than a half. So I definitely need to make theta small enough to make this work. Okay. So that's just hopefully highlighting why this is so important. And so as a final corollary, which I'll write here, this space CR alpha is preserved under this standard surgery. As long as, say, B is large enough, lambda is large enough. So say we, so from now, we can fix lambda equal to 10 and K naught equal to 2. K naught, I can't remember what that is. I think I meant just K. And so I guess we're not quite done, right? So at least when we bend it in and we choose this function u to be r naught times f, everything's fine, but there's also an interpolation, right? Where we said n hat was phi n tilde plus 1 minus phi c tilde. But as long as we were close enough to a cylinder in the sense of curvature, right? So that the norm of the curvature minus the curvature of a cylinder is bounded by epsilon. Okay, so we've got this this happening. As long as that's true, then I mean this n tilde is going to be very close to this c tilde, right? So this is already going to be close to n tilde. And so eventually you get the same estimates, right? Because if we're close enough in a high enough for high enough derivatives, then it should be fine. So not much detail, but so I'm sorry about that. But I'm hoping that at least this computation serves to see why we want to prove this estimate. And I'm hoping that you at least see somewhat how to get there. There's very little detail in the paper, so I struggled immensely, but hopefully we get some idea. So yeah, sorry that it was a little bit rough towards the end there, but now we've successfully, in quotes, got a surgery procedure that preserves CR alpha. And so from here, what we have to do essentially is prove that our cylindrical estimates hold across these surgeries. So I'm guessing maybe the canonical parameterization might come in handy there as well. So presume we need our cylindrical estimates. We also need to take care of these degenerate neck pictures. So remember, you've got these nice cylindrical things happening as long as your lambda 1 is small. So as long as lambda 1 on H is small, then these cylindrical things will happen. But what if it's not small? What if it's large? You've got this kind of convex cap forming. And this is where you need to use those gradient estimates. So I can't remember what it was. It was something like that. And so you need to be able to use these gradient estimates to prove that there's at least some sort of neck in the vicinity of this cap. So that's another technical thing we have to take care of if we're going to set it up with surgeries properly. From there, then you also need to show that the surgeries don't accumulate. I guess one detail I skipped today was the topology of the situation. cutting necks basically is like doing a reverse connect sum. So you have to show that. I don't think it's too hard though. And the paper skips over it quite quickly. But yeah, that's probably all I have to say today. Thank you.
Awesome. Thanks, James. Let's thank our speaker. Does anyone have anything they'd like to ask James?
All more insightful things to say.
Yeah, I had a question. I got a bit confused about. Could you go back to your picture of the neck,
Yeah,
like the deformation? Because there's like several different ends in the paper, and so what is the n tilde? You take your original n and then you bend it a little to start with.
Yeah, so you move down the normal via some function, and this
So why can't
will end
you
up
just
being that exponential.
Why can't you just interpolate between your original n straight to the n, the parameterization of the approximating cylinder to begin with?
So yeah, it's a good question. I think you want to get something strictly convex in this region, 2 lambda to 3 lambda. I don't know why actually. Why do you want strict convexity? Could there be problems with the interpolation if it's not strictly convex? I'm not sure.
Yeah, because well, I mean, you're putting in like just a half sphere kind of thing as the cap, right? Is that right?
Yeah.
Well, okay, actually, maybe. Okay, I'm not. Yeah, I'm not sure. It's kind of hard to read from the paper, and I don't know. I mean, this is kind of a question for just a general question. Maybe if someone in the audience knows the answer. So in the end of this whole section, you prove that the surface remains in CR alpha after the surgery, and in the later estimates, like the convex estimate, cylindrical estimate, gradient estimate, all the constants only depend on R and alpha. And well, actually, it only depends on N and alpha, and R is already there. So why do you need to do extra work to prove those estimates in the presence of surgery? Because, well, you already know that they're true because your surface is already in CR alpha after surgery. So, but in the paper, there's like a lot of extra effort that's put into trying to prove these estimates in the presence of surgery. I'm not sure if anyone knows the answer to that question, but
I should know the answer. I could try to answer it. Yeah, so I think the first points you raised might be answered a little bit by the second part. So you do have to construct these necks so that they're controlled, so that your estimates don't degenerate across the surgery. So that may have something to do with the getting it convex in that region.
But I was just thinking that the estimates seem to only depend on R alpha. So if you're still in CR alpha, then yeah, it should be the same, right?
No, not quite. Let's see. There's I'd have to think about it. I've forgotten exactly how it goes. But that's
yeah, it's all good.
You have to preserve the initial. It's not just preserving the initial thing. It's a little bit tricky, especially the gradient estimates.
Yeah, the gradient estimates are over a later time, aren't they? Or is that?
Yes.
That's true, isn't it? Yep.
But also the convexity estimates and the cylindrical estimates, you have to do this Stampacchia iteration thing. So again, it's not just a maximum principle preserving the initial value. It's a bit more subtle than that.
Okay.
So you have to do the integral estimates across the surgery times.
Okay.
Yeah, sorry, that's not the best. There's a better answer, but let me think about it. Maybe I'll catch you next week.
Thanks.
James, I had a question for you.
Mm-hmm.
This might sound like I'm putting you on the spot, but I'm actually just curious. Did you go through Hamilton's, existence argument for these CMC foliations? Because I know he tends to be very brief with these things.
I started and I read about 2 lines into the proof, and I was already like, I had no idea how he was coming up with this certain argument. So basically, I started with uniqueness, right? And what he had was this diffeomorphism between the cylinders, and then the idea was you've got this CMC foliation, right? And basically, he made this argument in a couple of sentences that the diffeomorphism preserves this CMC foliation. And I spent about a day thinking about that, and I could not figure out how on earth that would hold for a general diffeomorphism.
Well, I guess
I
mean, I guess it comes down. Does it come down to the existence and uniqueness of the CGC foliation itself?
Yeah. So you've got this unique family. The diffeomorphism preserves the boundary of the cylinders.
Yeah.
And then the argument is because it preserves the boundary, it's also going to preserve the nearby, like the nearby leaves of this foliation. But it doesn't seem plausible to me, to be honest. Like just take an annulus in R3. And take a diffeomorphism of that preserves the inner and outer shells. And as long as it swirls around the inside enough, it's not going to preserve the concentric spheres. So, I mean, yeah, I don't know.
Yeah.
It was a bit hard.
Yeah, maybe. So it feels like it's all just inverse function theorem, isn't it? Isn't that what he says?
It's littered throughout. Yeah, absolutely.
Yeah.
And these harmonic maps and things, and
yeah. It's interesting because Hamilton's clearly aware that some inverse function theorem arguments are very difficult because he's dedicated an entire article to a certain version of the inverse function theorem, and yet other times he decides that a sentence is enough.
Yeah, absolutely.
Is that from the survey article?
Yeah, that's what I was referencing. Yeah, on the Nash motor.
I mean, for the CMC foliation thing.
Oh, the CMC foliation. Which reference were you using of that, James?
Let me check.
I mean, the stuff that Hamilton's done that I'm aware of, where he does CMC foliations, is in his 4 manifolds with positive isotropic curvature paper. He does it there, I think.
I think that's what it is.
Yeah.
That's where this surgery, this canonical parametrization is defined as well, and the surgery procedure.
Yeah. Good.
So this is all just Hamilton's thing, but adapted to the extrinsic case.
Yeah. Cool. Any other questions for James? All right, then. Before we thank James one more time, I'll just mention casually that James has done his oral examination for his PhD, and hopefully that'll be conferred soon. So maybe within a couple of weeks, he'll be Dr. Stanfield. And he'll be moving to Germany next year for a postdoc position. So hopefully you'll still remember our little seminar here in Australia and be happy to contribute when the time arises. All right, let's thank James again.
Thanks, everyone.
Thanks, James. Great work. Hard
Thanks,
stuff.
Matt.
All right, I'll stop the recording there.